So, welcome back everyone to week 9 of our Calculus with Python series. Last week we established the crucial concept of limits, understanding how functions behave as inputs approach a certain value. And today we build directly on that foundation to explore derivatives. We will learn how derivatives measure instantaneous rates of change, how they relate geometrically to slopes and tangent lines, how to use basic differentiation rules, and how to compute them symbolically using Python's sympy library. We will also introduce the concept of the gradient for functions of multiple variables and discuss again why derivatives are absolutely central to AI optimization and relevant in quantum computing. But before we start, I'd like to mention that it's a super friendly and inclusive space. Let's encourage each other and lift one another up. Please maintain a professional and friendly attitude. If something doesn't feel right, let the host know during the event or reach out via email. We are here to make sure everyone feels comfortable and included. Feel free to ask any questions at QA session or via our Discord channel. Any questions are welcome. This event session will be recorded. So, here's our roadmap for today. We will quickly recap why limits are essential for understanding derivatives. We will define the derivative conceptually as the instantaneous rate of change. We will spend time on the geometric interpretation. The derivative as the slope of the tangent line to a curve and visualize this with Matplotlib. We will revisit the formal Leavitt definition of the derivative, connecting it to the geometric view. 3 blue, 1 brown is great for this also. We will introduce some essential shortcut rules for differentiation, covered extensively on Khan Academy. We will learn how to use the Python library sympy to compute derivatives symbolically, looking at several code examples. We will then extend the idea to functions of multiple variables, introducing partial derivatives and the gradient vector, including a visualization. We will reinforce the significance of derivatives and gradients in AI, especially gradient descent and quantum computing. We will summarize the key concepts, and finally, I'll suggest some practice exercises and, of course, resources. And just a quick reminder from last week. We learned about limits. The lim of f of x as x approaches c equals L. All this tells us the value L, that the function output f of x gets arbitrarily close to as the input x gets arbitrarily close to c. The idea of the investigating what happens as the things get infinitesimally or arbitrarily close is precisely the tool we need to move from average rates of change to instantaneous rates of change, which is what derivatives are all about. So, what is derivatives conceptually? It's a fundamental tool in calculus that measures the instantaneous rate of change of a function. While we can easily calculate an average rate of change over an interval, like average speed over a trip. The derivatives tells us how fast the function's output is changing at one specific instant or point of input. Think about familiar example. If you have a function describing an object's position over time, say f of t, its derivative, which we often write as f prime of t, represents the object's instantaneous velocity at that exact moment t. If you have a cost function, C of Q, for producing Q items, its derivative, C prime of Q, represents the marginal cost, broadly, how much more it costs to produce just one additional item at that production level Q. The derivative gives us the precise rate of change at a point. Geometrically, the derivative relates to the concept of slope. Let's start with the average rate of change between 2 points of the function's curve. If we have 2 points, say at x and x plus h, their corresponding y waves are f of x and f of x plus h. Let's take a look at this example. This code defines a sample function f of x equals x squared plus 1. It picks two x values, x0 and x1 equal x0 plus h, calculates the corresponding y values and plots the function curve, later blue. And these 2 points, red dots, later at the next slide you'll see this on plot. This second line is the straight the line passing directly throughout these 2 points. So let's take a look. The plot shows the slope calculated for the chosen points. The slope of this second line represents the average rate of change of the function between x0 and x1. We calculate it using the standard rise over run formula, the change in y divided by the change in x. Here the change in y, delta y, is x of f of x0 plus h minus f of x0. And the change in delta x is simply h. So the slope is f of x naught plus h minus f of x naught divided by h. Now, how do we get the instantaneous rate of change? Imagine the second line from the previous slide. What happens if we make the distance h between the 2 points smaller and smaller, effectively sliding the second point along the curve forward the first point? As h approaches 0, the second line pivots and gets closer and closer to becoming the tangent line, the unique line that just grazes the curve at that single point, x equals c. The slope of this tangent line represents the instantaneous rate of change of the function exactly at that point where x equals c. And this is the geometric meaning of the derivative. The derivative of f at point C, f prime of C, is the slope of the tangent line to the graph of y equal f of x at the point where x equals c. This code plots our function f of x equal squared x plus 1 again. We choose a point of tangency c equal 1.5. We know from differentiation rules, we will see a little bit later, that the derivative f prime x is square to multiply x. So the slope at c equal 1.5 is f prime 1.5 equal 2 multiply 1.5 equals 3. The code calculates the slope and uses the point slope formula to define and plot the tangent line. And on the next slide, you'll see it will be green line passing throughout the point C and F of C. It will be green dot with that exact slope. So you can see how the green line just touches the blue curve at the green dot. The commented out code shows that a second line with a very small h would be almost identical to this tangent line. The connection between the shrinking second line and the tangent line slope is formalized by the limit definition of the derivative. This definition shown on the slide is fundamental. Let's read it. F prime of x equals the limit as h approaches 0 of the quantity f of x plus h minus f of x, all divided by h. Let's break it down. The fraction part is exactly the rise over run calculation we saw for the slope of the second line between points x and x plus h. The limit as h approaches 0 part tells us to take the limit of the slope as the distance h between the 2 points shrinks down towards 0. The result of this limit, if it exists, is the derivative f prime of x, which represents the slope of the tangent line at x, giving us the instantaneous rate of change. This limit definition precisely captures the idea of finding the slope at a single point by seeing what the slopes of nearby second line approach. The 3-Blue-1-Brown Essence of Calculus series has a fantastic visual explanation of this limit definition. Calculating derivatives using the definition every time would be tedious. Thankfully, mathematicians developed shortcut rules for differentiation based on the limit definition. Here are some fundamental ones. Constant rule. The derivative of a constant function like f of x equals 5 is always 0. This makes sense as the graph y equals 5 is a horizontal line and its slope is 0 everywhere. Power rule. This is essential for f of x equals x to the power of n. The derivative f prime of x is n times x to the power of n minus 1. You bring the old power down as a multiplier and reduce the power by 1. For example, the derivative of x squared is 2 times x to the power 1, which is just 2 times x. The derivative of x cubed is 3 times x squared, and constant multiple rule. If a function is multiplied by a constant, like 5 multiply x squared, you can just pull the constant out. Finding the derivative of the rest 2 times x and multiply the constant back. 5 multiply 2 times x equals 10 times x. The notation d divide dx means the derivative with respect to x. So, as dx of k times f of x equals k times f prime of x. And last one, so difference rule. To differentiate a function that's a sum of difference of terms, like x cubed minus x, you can just differentiate each term separately and keep the plus or minus sign. Dx of f of x plus or minus g of x equals f prime of x plus or minus g prime of x. There are more advanced rules like the product rule, quotient rule, and the very important chain rule for handling more complex functions, but these basic ones cover many common cases. Khan Academy is an excellent resource for learning and practicing all these rules. While understanding the rules is important, we can use Python libraries to perform differentiation symbolically, meaning it gives us the exact mathematical formula for the derivative, not just a numerical value. The primary library for this is sympy. Using sympy generally involves these steps. We need, first of all, import the library at the line import sympy. Define the symbolic variables you need to using sympy.symbols. For example, x equal sympy.symbols x. Tells sympy to treat x as a mathematical symbol, not a regular programming variable holding a number. Next, define your function using these sympy symbols. The operations look like a regular math: plus, minus, multiply, divide. Use the sympy.diff for differentiate. To compute this function, used to compute the derivative. You pass it the function expression and the variable you want to differentiate with respect to. Let's see some examples. Let's use sympy to differentiate some simple polynomials. So let's explore this code. We first define x as a symbol using sympy.symbol x. Then we define our first function, f1 equals x squared. We compute its derivative with respect to x using sympy.diff of f1, comma x, and store it in f1 prime. Printing f1 prime shows the result 2 times x or 2x, which matches the power rule. And next we define f2 equals x cubed minus x. We compute its derivative f2 prime, which equals sympy.diff f2 and x. Printing f2 prime gives 3 times x squared minus 1, which correctly applies the power rule and sim difference rule term by term. Sympy handles these basic rules automatically. Sympy easily handles constants and allows evaluating the derivative at specific point. So let's explore this part of code. We define x as a symbol, then we define the function f3, which equals 5 times x cubed plus 2x minus 7. We define its derivative f3 prime, which equals sympy dot diff f3 and x. Printing f3 prime shows 15 times x squared plus 2, correctly applying the power rule, constant multiple rule, sum difference rule, and the constant rule. Derivative of minus 7 is 0. Now, how do we find the slope, the derivative's value? At a specific point, say x equal 2, we take the derivative expression f3 prime and use its subs function for substitute. We call f3 prime subs x and 2 to substitute the symbol x with the value 2. Printing the result, slope at 2 gives 62. This is f prime of 2. The slope of the tangent line to f3 at the point where x equals 2. Calculus isn't limited to functions of one variable. We often deal with functions that take multiple inputs, like f of x and y, where the output depends on both x and y. Think of the higher on a hill depending on your east, west, x, and north, south, y position. How do we talk about the rate of change for such functions? We use partial derivatives. Partial derivatives is a derivative with respect to one variable while treating all other variables as if they were constants. The notation uses a curly D symbol, like partial f, partial x, or sometimes del f, del x. This tells us how fast f changes if we only move in the x direction. Let's take a look at next example. Sympy handles this easily. We define multiple symbols xy equals sympy symbols xy. We define a function f multi involving both x and y, like x squared times y plus sine of y using sympy dot sign. To find the partial derivative with respect to x, we use sympy.diff, f multi and x. Sympy treats y as a constant, giving 2 multiply x multiply y. Derivative of x squared is 2 times x, y is a constant multiplier. Derivative of sin y with respect to x is 0. To find the partial derivative with respect to y, we use sympy.diff f multi y, where sympy treats x as a constant, given x squared plus sympy cos y. Derivative of y is 1, and x squared is a constant multiplier. Derivative of sin y with respect to y is cosinus y. The gradient of the function y, function f, written at nabla f of grad f, is simply a vector that collects all the partial derivatives together. This vector is incredibly important because it points in the direction where the function f increases most steeply at given xy points. Its length magnitude tells us how steep that increase is. The gradient vector, nabla f, has a nice geometric interpretation. It always points in the direction of the steepest ascent of the function at that point and is perpendicular to the contour line, the line of constant function value passing throughout that point. Let's visualize this for the simple function f of x, y equals x squared plus y squared. Its level curves and circles centered at the origin. This code first uses sympy to find the partial derivatives of df dx and df dy. Then it sets up a grid of xy points using numpy.meshGrid to calculate the function value z across the grid. It calculates the specific gradient vector components at the point 1, 1 by substituting x1, x equal 1 and y equal 1 into the derivative expressions, giving 2, 2. The core plotting uses plot.contour to draw the contour lines, circles in this case, and plot.quiver to draw the gradient vector as an arrow starting at 1, 1. The plot shows the circular contour lines of f x y equal x squared plus y squared. The red dot marks the point 1, 1. The red arrow starting from the point is the gradient vector. Notice how the arrow points directly away from the origin, the minimum value of the function, which is the direction of steepest increase. Also observe that the red arrow is perpendicular to the circular contour line passing throughout 1, 1. This visual confirms the properties of the gradient. Let's explicitly revisit why derivatives and gradients are so critical for AI and quantum computing. For AI, exactly gradient descent. Remember, training often means minimizing a loss function. Gradient descent does this iteratively. At each step, it calculates the gradient, nabla f or grad f. of the loss function with respect to the model parameters. This use of the gradient is the absolute core of how most deep learning models are trained. For quantum computing, optimization also plays a role in quantum computing. For instance, variational quantum eigensolvers are algorithms used to find the ground state energy, minimum energy of molecules, often involving classical optimization loops that use gradients to tune parameters in a quantum circuit. So, understanding derivatives and gradients is essential for understanding optimization in AI and the dynamics described in quantum computing. Let's summarize. The derivative f prime of x measures instantaneous rate of change and represents the slope of the tangent line geometrically. The limit definition involving h approaching 0 is the formal foundation, visualized well by 3 blue, 1 brown. We use differentiation rules, power rule, detailed on Khan Academy as shortcuts. Python's sympy library using sympy.diff allows us to compute derivatives symbolically. For functions of multiple variables, the gradient nabla f is a vector of partial derivatives and points in the direction of steepest ascent. This is fundamental to gradient descent optimization in AI. We saw how Matplotlib helps visualize secant lines, tangent lines, and gradients, aiding intuition. To help solidify these concepts, here are some practice exercises and resources for further study. The resource links point to Khan Academy, the excellent 3 blue 1 brown calculus series for intuition, and the official documentation for sympy and Matplotlib. Experimenting with the code is the best way to learn. Please review the basics differentiation rules on Khan Academy. Use sympy to practice finding derivatives symbolically. Try the examples listed, maybe even one like x times sympy.exp of x to see sympy handles the product rule automatically. Practice evaluating derivatives at points using sympy.simps to method to find slopes. Use Matplotlib to visualize a function like x cubed and plot its tangent line at a specific point. Try calculating the gradient vector nabla f for a simple multivariable function like f of x y equals x times x using sympy. That brings us to the end of today's session. Thank you all for your participation. It was great to have you all here. If you have any question at all, don't hesitate to reach out on our community Discord channel. This session was recorded and will be available on our GDG Ahlen YouTube channel later. So if you want to review anything we covered, feel free to rewatch it at your convenience. I really appreciate if you could take a few minutes to fill out the post-event feedback form. Your feedback is invaluable in helping us improve and make future sessions even better. Once again, thank you for being together, for joining. See you in our next session next Sunday. Until then, keep learning, experimenting, and building with AI.